Okay, so hello everybody. I hope you had a good lunch, good rest. This lecture will be about nanotechnology for water purification. After this lecture we should have a tutorial, but I told Professor Patra that I don't have any tutorials, so we're going to have an open discussion. If you want to discuss something, I can tell you about other research projects in my lab. Whatever you want to do. But I don't have a tutorial. Anyway, so the lecture of now will be about nanotechnology for water purification. In this lecture, we will talk about some things that I already discussed this morning. So some concepts you might be already familiar with. For example, carbon dots. We will talk a little bit more in details about carbon dots and how beautiful things we can do with carbon dots. But we will start with filters. Nanofilters, two-dimensional nanofilters will introduce interesting nanomaterials in two-dimensional films that we can use for water filtration. Then we'll talk about metal nanoparticles for water purification. And then I'll describe actually some things that we did in my lab in the last few years using carbon dots for water cleaning in general. Okay, how we clean water. So the easiest thing to clean water, if you think about it, is just like we do anyway. You have a filter. You take water from one side. The filter is supposed to collect all the dirt, all the pollution, all the bad things in the water. And then on the other side, you're supposed to have drinking water. Actually, these kind of filters are very common in many water cleaning devices and water cleaning instruments. Sometimes you can buy them in the shop. What nanotechnology can give us are special nanofilters. And the nano here, the small dimension, what it gives us is a way to do excellent filtration. To filter the smallest particles, to be able to filter all the bad molecules. It's just very efficient filters. This is actually one of the most interesting two-dimensional nanofilters. This is called graphene. Graphene is also a form of carbon. Today we talked a lot about carbon. Why we like carbon? Because it's cheap. We can find it everywhere. And good for us, we can make very easily or relatively easily, we can make different things from carbon. This is one of the things that we can make from carbon, graphene. Now, graphene is just a big sheet of carbon that connected in a hexagonal way in a 6-membered ring. And what's special about graphene, there's many things that are special, but the most important properties of graphene is that it's very, very thin. It's so thin that the thickness is sometimes, depending on the graphene, 1 or 2 or 3 atoms. So basically you can take many graphene, many carbon atoms in the 2 dimensions. In the 3rd dimension, it's very, very thin. That actually makes graphene sheets very special, very light for one thing. You can easily bend them without breaking, just like you can see here. This is actually a real picture of a graphene sheet. Now, obviously, this graphene sheet is not 1 or 2 atoms thick. Otherwise, we will not be able to see that. But still, this graphene that this person is holding is less than 10 micron. Very, very thin. The other nice things about graphene is that it is extremely strong. Very difficult to break it and to tear it. This is because of the special chemical properties and chemical organization of the carbon. All these bonds, these double bonds, are very strong. So overall, the graphene is very, very strong and not breakable. The other thing that's remarkable about graphene, and actually we use for water purification, is that it is conductive. It's very conductive. It's conductive for electrons, so it can conduct electricity. In a minute, I'll show you why it is important. But actually, one of the applications that people use these days with graphene is just for electronics, carbon electronics, because it is such a good conductor. So how can we use graphene as a filter? Now, first of all, it's very thin, so we can use it as a membrane to filter. Now, because the openings here are very small, basically what we have is that water can go through these holes here. Okay, see a drop of water. But if you have bigger things, like nanoparticles, like microparticles, remember those nanoplastics and microplastics that we discussed before lunch? So when they go in, they can just get stuck here and don't go through. The same for other things, contaminants that might be in the water. Now, because graphene is so strong, so stable, you can pass water with pressure. It will do the filtration, but it will not break, which is something very important. Now, another very important thing about graphene as a filter is the fact that it is conductive. Remember, we said that graphene can conduct electricity. Now, why it is important? Remember that we talked before lunch about oxidation. When we have pollutants in the water, we can oxidize them. And when we oxidize them, we break them. Now, because graphene is such a good conductor, we can connect it like this to some kind of electrolyzer. We can pass electrons in these graphene sheet. And then, when you have pollutant molecules coming closer to the graphene, they can get oxidized. Okay, sorry. They can get oxidized, and then we can remove them from solution. We break the pollutants, we degrade the pollutants, and remove them. So graphene can both filter and also use for oxidation of organic pollutants. Very effective filtration. Actually, the other nice thing about graphene, and graphene conductivity in particular, is that when we have ions, metal ions, somebody before lunch asked about heavy metal ions, like iron, copper, lead, all these really bad things that you can find in the water. Now, these ions can be in the water. Again, when they get closer to the graphene sheet, and graphene has all these electrons, you can get the electrons and reduce the positive ion or oxidize the negative ions. And then what happens is that these ions, because of the reduction or the oxidation, they become metallic and they aggregate and they sit on the graphene and they don't go through. So that's why graphene is such a good membrane, such a good filter. It can filter out particles, it can oxidize organic pollutants, and it can reduce or oxidize heavy metal ions and then aggregate them and remove them from water. There are actually already commercial products of graphene that we can use in water filters. They're a little expensive, but the process for making large-scale graphene are becoming very effective, relatively cheap, so we can use them in water filtration. This is another example of nanomaterial used for filter or nanofiltration. This is also involving the cellulose. Remember our good friend cellulose, the nanocellulose? So we can actually make another assembly of cellulose. This is called hemicellulose. Basically, hemicellulose are many cellulose nanofibers that are organized like this or like this. And what it makes a very good membrane, okay, that can capture both pollutants or particles, anything that you don't want to have in your water. And when you pass water, polluted water, in this hemicellulose nanofiber, you can clean the water. Very nice. Now, let's talk about nanoparticles. In many cases, as we saw before, as we talked before lunch, nanoparticles, particularly metal nanoparticles, can oxidize molecules. So the oxidation that they can do can be both for organic pollutants, but you can actually also oxidized microorganisms like bacteria. So the effect of taking electrons and destroying molecules can be done also for entire microorganisms like bacteria. And then what you get nanoparticles, particularly metal nanoparticles, that are antimicrobial. This is very important because in some cases we have contamination of bacteria in drinking water. So you can take the water, you can mix it or pass it through nanoparticles, through metal nanoparticles. These metal nanoparticles will oxidize the bacteria and kill them. Very good. Let's talk about magnetic nanoparticles. How do you think we can make magnetic nanoparticles? What elements we can use for magnetic nanoparticles? Iron, manganese, all the metals that form magnets. Indeed, we can take iron and make small nanoparticles of iron, and then these nanoparticles will be magnetic. Now, why it is good to have magnetic nanoparticles? If we have magnetic nanoparticles, we can control them externally with a magnet. Okay? Just like we have here. If these nanoparticles will be magnetic, we'll have a magnet, in this case, outside this container, and all the nanoparticles will come towards the magnet. Very simple. What we see here is actually a very simple way to clean water. Because what do we do? Let's say we have polluted water. Water with lots of bad molecules, bad particles, whatever. Then we take and put magnetic nanoparticles inside this water. Okay? We put it in the water, we mix it, we shake it. The magnetic nanoparticles will absorb various contaminants through the fact that there is surface area or oxidation. And all the pollutants will absorb on the surface of the nanoparticles. Now the question is, okay, so we have water, we have pollutants absorbed on the magnetic nanoparticles. Now the question you can ask is, okay, but now we have to clean not only the pollutants but also the magnetic nanoparticles. How will you do that? This is why we have the magnet. We take the magnet, put it from outside, all the magnetic nanoparticles with the pollutants absorbed on their surface, they will attract to the magnet, and then we take all the water, we pour it out, and this water will be pure. So the fact that we are dealing with magnetic nanoparticles give us a way to purify the water from the magnetic nanoparticles and the contaminants. This is actually a common technique that people use in industrial settings. So this is, for example, magnetic nanoparticles with contaminants. We can pass the water through this container. Then we're going to put a magnetic rod. Just put a rod inside the water. All the magnetic nanoparticles and the contaminants will stick to the rod. And what we have here, just purified water. Now, nanoparticles can be also very good photocatalysts. Remember, when we talked about photocatalysis, what we have is light generating electrons, light hitting the nanoparticles, giving energy for electrons to leave the nanoparticles and oxidize. What the light is doing is, when we have organic pollutants, the electrons that we generate with light, they will go and break the organic pollutants. This is big organic pollutants, big molecules, and after doing the catalysis, after breaking the bonds using light, we can get these simple building blocks that are not bad. Okay? So this is photocatalysis of organic pollutants. We can see it here, the concept. We have wastewater, dirty water, water with various organic pollutants. We put inside the water photocatalyst, nanoparticles that are able to generate electrons because we shine light on them. In some cases, actually, when you shine light, you can get oxygen from the air that gets reduced, And this oxygen is actually a very good catalyst. So the catalyst can be either the nanoparticles themselves or oxygen that becomes oxidative, becomes a catalyst. And following the activity of the oxygen or the nanoparticles, we break the organic pollutants and we get clean water. This is an example of photocatalysis, purification of water with light. Let's go back to the story of the carbon dots. Okay, and I'll tell you about two very interesting applications of carbon dots for water purification. So let's talk a little bit more deep on carbon dots. Before lunch in the morning, I gave you a very general introduction on carbon dots. Let's talk more specifically on their very interesting physical properties. So these are carbon dots. Basically, it's just like a ball made of these 6-member rings. Just like graphene. Remember graphene? The graphene sheet? So carbon dots are basically little particles, graphene particles. So actually, when people refer to carbon dots, sometimes they call them graphene quantum dots, because the structure, the internal structure of the carbon dots is very similar like graphene. These 6-member rings, which actually means that also carbon dots will be conductive, electrically conductive. This is how the carbon dots look under electron microscope. You see very small dots, very small nanoparticles. And if we look closely on the carbon dots, you see these lines here. These are exactly the sheets of graphene. Okay? The same atomic structure, also the same organization of graphene sheets. Now, this is not why carbon dots are so interesting. Just remember, to make carbon dots, very easy. That's why we also like them. Because when you have an easy chemical system, an easy preparation, it's always better compared to complicated chemistry. So we can make carbon dots basically from any carbon source. Now, the first reason that people really like carbon dots are the colors. When people first discovered carbon dots about 30 or 40 years ago, what they found was that carbon dots have remarkable colors. You can get from purple all the way to red. Now, this is actually very strange. When you think of carbon, when you think of coal, for example, coal is also pure carbon. When you think of a pencil, you know pencil? You know what's we use for writing in a pencil? Graphite. Graphite is also pure carbon. Does graphite have a color? I don't know if they have a color. Graphite is black. Coal that you burn in power stations is also black. Suddenly we have carbon that has a color, just like a rainbow. This was really surprising. The reason why carbon dots have color actually, and not only that they have color for the entire spectrum, is precisely because of the size. Because they are so small, you can have color. And this color is actually because of a very special property called fluorescence. Have you heard of fluorescence? These colors are fluorescent colors. So you get them if you shine light on the carbon dots. And the reason you get colors of carbon dots when you shine light is precisely because electrons can jump from low level to a high level. Now, these are not carbon dots, these are semiconductor quantum dots. Semiconductor quantum dots are the first nanoparticles that people discovered about 50 years ago. The color of semiconductor quantum dots is actually related to the size. If you have a big size, you excite the electron to a low level, it goes back, it gives you red color, and this one gives you blue color. But it gives you color. With carbon dots, actually, the color is related to the fact that you excite electron from the inside of the carbon dot to the surface of the carbon dot. When you excite the electron from the core to the surface, and because the carbon dots are so small, you can get visible color. And the reason you have different colors is because the surface of the carbon dots is not completely uniform. You have various chemical groups on the surface that give you different colors. So this is very interesting. Does it have to do with water purification? No. This is just the reason why people became very interested about carbon dots. And actually, they can use the colors for various things. For example, sensing. You can use the color for sensing. You can use the color for labeling bacteria and cells, for example. But this is a different story. Our story is not color, but is related to the fact that when you shine light on the carbon dots, what you do, when you shine light, remember this slide, when you shine light, you excite the electron from low level to high level. Now, when you excite the electron from low level to high level, what does the electron want to do? Go back. In nature, always the desire is to go back to the initial stable sort of situation. So, the electron, you excite it with light to a higher level, it wants to go back. The easiest way to go back for the electron is to jump right back. When it jumps right back, it gives us the color, these beautiful colors. And this is what happens in solution. But when you have solid, when you take carbon dots and they cannot move and they sit in solid matrix, either when you dry them or when you put them in some kind of solid gel matrix, then the electron that you excite cannot go back directly because of the solid phase. Instead, what happens is the electron will go back indirectly. It will go back from here to other levels that the electron finds in the environment. And this process generates heat. And that's the key thing, as we're going to see in a minute, in these water purification applications. This is called a photothermal effect. Light-induced heating. So remember, the key thing, the important thing is carbon dots in a solid phase, they don't have color. But when we shine light, they generate heat. This is called in the physics language, multi-phonon radiation. This is a thermal effect. Okay, so we have a photothermal effect. Let's see how it helps us. And what I'll show you are two interesting applications of the photothermal effect of carbon dots for water purification. Now, why do we need water purification? Because water is, or finding clean water is not so easy these days. Either we live in a desert, or that there's not enough water, or if we live in places where the water is polluted. In both cases, we don't have enough drinking water. We need drinking water. Now, there are a lot of water purification technologies these days. People use what's called reverse osmosis. There are membranes here that when you pass the water, you clean the water, very nice. There are ion exchange, something that you use in your labs. When you want to clean water, you pass the water in big column. That's how you clean the water. So if we have these technologies, what's the problem? Why do we need something new? The problem with these technologies is that, for one thing, they can be very expensive. For example, this technique, reverse osmosis, needs a lot of energy, a lot of electricity, which is expensive. This technique is usually not so efficient. So you have these big columns, you need to replace them every few months, for example, and there's other problems. So there's always a search for new technologies. Desalination, that's what we want. Let me describe the system that we made in our lab for water purification or water desalination. Now what we do, we took carbon dots, we mix them with two very cheap polymers. One is called chitosan, actually very simple polymer that you can also find in plants. And this is CMC, methoxycellulose. It's also a very cheap and simple polymer. And when we mix them all together, we obtained a sponge. Okay? Just a sponge that you can look at it. Let's see if I have a picture. That's how it looks. Let's see, wait. No, I don't have a picture. But this sponge is very easy to make. The good thing about this sponge is that it can absorb water. So you can use it as a filter. Now what's the secret here? You have the sponge. We pass the water in the sponge. Water goes into the sponge, just like a membrane, just like a filter. And then we shine light. Now what the light will do, remember the photothermal effect. Light gonna get absorbed by the carbon dots. Now the carbon dots in this case are in solid environment. They are sitting in the sponge. Now remember, when the carbon dots are in solid environment, they release heat. We shine light, this becomes hot. It becomes hot and more hot and more hot. What happens to the water when it gets hot? They evaporate, exactly. When you heat water, they evaporate, just like steam. The water gets evaporated. Now it's pure. There's no salts, there's no contaminants, there's no anything. You just need to collect the vapor, you just need to collect the steam, and you have clean water. Fantastic. Let's show you evidence that it's really happening. Okay? So we took carbon dots that can absorb light in a broad range. That's how it looks. Okay? This is actually the polymer that is porous. Looks like a sponge. So we see that this polymer is made of these big fibers. And if we look, it's very porous. There is lots of space for water to come in. Remember, we want a lot of water to come in because we want to clean, to purify a lot of water. Okay, so this is how it looks. This sponge without carbon dots, and this is with carbon dots. And the black color, the brown actually color, tells us that there are carbon dots there. We cannot see them in this picture because they're very, very, very small. The scale here is 50 micron, so they're sitting all over the place and they make the sponge black. Now look at this beautiful picture. What we see here is images of a photothermal camera. Do you know how a photothermal camera works? When something is hot, it gives us red color. Actually, a photothermal camera allows us to take pictures in the dark, at night. Because, for example, when people or animals are outside in the dark, they emit heat, and you can see that with a camera. This is actually, another application is in war. You have binoculars that are sensitive to heat, to IR. So what we see here, these are photothermal images of just this simple polymer without carbon dots. Remember, the more red color, the more hot. So here we shine light, and after 60 minutes, we see some red, and the temperature, 28 degrees. Do you think it's a high temperature? It's not such a high temperature. It will not evaporate the water. But when we look at these pictures here, this is this gel, this sponge, with carbon dots. Remember that the carbon dots are doing the photothermal effect. So we irradiate, we shine light for 0, 15 minutes, 30 minutes, 60 minutes, and within 60 minutes, look at the temperature. The temperature now is almost 60 degrees. Much higher temperature than this gel without carbon dots. What we see here, these colors compared to these colors, is exactly the photothermal effect of the carbon dots. They absorb light, they make heat, they heat the gel, and the water will evaporate. Okay? These graphs show you how the temperature is going up when you have carbon dots inside the gel. Now, what can we do with this? What we see here are graphs of using this gel, this concept, for cleaning water. So we took now water with different contaminants, different ions, heavy metal ions, very bad for our health. But when we do this photothermal effect, this heating, we can clean the water almost from 100% of the contaminants. What we see here is removal of the heavy metal ions. We can also remove organic contaminants, organic pollutants. You can see here that after we make water with some organic pollutant, it's called SDS, But after passing in this gel, we get pure water. This is another example of an organic pollutant that has a color, a visible color. It's called R6G. You see very high absorbance. You get water which are actually red with this polymer, with this contaminant. But again, after we purify the water with our special gel with carbon dots, nothing. We cleaned the water completely. Very nice. Another story. Using the carbon dots for oil spill cleanup. Now what we see here, sometime, unfortunately, there is oil spill on the ocean or on lakes or on rivers. When you take oil and you spill it, it goes and covers the water. It kills the fish. It kills bird. It's really bad for us. You know how you clean oil spill now? It's very, very difficult. What you need to do, because oil is very sticky, what you do, you take people or a ship, okay, and you just dip some cloth or some sponge or something, and you just simply need to collect the oil. This is very hard work because oil is so viscous. So it just stays. It's hard to do physically. And there's no technologies that can clean oil from water very effectively. There's some people that put chemicals that break the oil, but this is not so efficient, and it can also contaminate the water with chemicals. Some people put bacteria, some technologies put bacteria, which is also very inefficient. So this is a problem. How to develop technologies for cleaning oil from water. And the problem is, or the core of the problem is that oil is very viscous. Very hard to work with this. Now let me describe to you a very interesting solution that we developed in my lab. Again, that takes carbon dots and specifically takes the photothermal effect of carbon dots to develop technologies for cleaning oil spill. The concept here is very similar to what I described to you before. We make a sponge. This sponge is actually even more simple and cheaper than the previous sponge that I showed you. This is called polyurethane. You can buy it in the store. It looks like this. This is a real picture. It's just a very, very soft and flexible sponge made of polymer. Very simple to handle, very cheap. You can buy square or meter cubes of this, very cheap. Why I emphasize this is cheap? Because when we want to use it as something practical for oil spill, for example, we need something that's going to be cheap and available in large quantities. So this is the polyurethane sponge. What we did, we add carbon dots with some polymer which acts as a cross-linker. And what we get is a new sponge with the carbon dots sitting inside the pores, using the PDMS here as some kind of helper, some kind of cross-linker. The important thing is that now we have polyurethane with many, many, many carbon dots sitting inside. Now, you can see this is a real picture. That's how it looks. Carbon dots are kind of brown, dark brown. so we can see visibly that the carbon dots are inside. Now, the reason why we use polyurethane, there's two reasons actually. One reason that it's cheap. There's three reasons. One reason that it's cheap. Second reason is that it is very, very porous, meaning that you can have lots of liquid solution going inside. The third thing is that the surface of polyurethane is very hydrophobic. Why it's important for us to have a hydrophobic surface? Because we want oil. Oil is hydrophobic. So if we have hydrophobic surface, maybe the oil will go in, and then we take it and go home. But what's the problem? Oil is very viscous. So even if we take the polyurethane, the sponge here, it's very hydrophobic, and we dip it in the oil will not go in because it's so hard to move. It's so viscous. So what we need to do in order for the oil to come in, we need to make the oil less viscous. Do you know in the kitchen how you make oil less viscous? Certain oils, certain fat, how you make them less viscous? Heating. Try it at home. Next time you cook, or next time you cook, think about it. When you have fat, when you want to clean the oven or something, you need to heat the surface or to heat the pan in order to make the oil less viscous. So our idea here is, let's do the same thing. Let's try to make the oil less viscous, and then it will go very efficiently into the sponge. How we can heat the oil? With the photothermal effect of the carbon dots. Okay? So what happened? We have the sponge that is very porous with all the carbon dots sitting inside. We put this in the oil. We have the ocean. We have the river. We dip it in the oil. And then we have the sun. We shine light. Okay? What the sun will do, the light will get absorbed by the carbon dots, and then we have the photothermal effect. The carbon dots are going to release heat to the environment. The oil will be less viscous, and it will go very easily into the sponge. Then we take the sponge, we do like this, and all the oil goes out. And we clean the oil. Okay? Let's see if it really works. Okay? This is an example of experiment we did in the lab. Okay? So this is the sponge with the carbon dots. What we see here, we put the sponge in the oil. We actually put little color so we see the oil more clearly. So we put the sponge inside the oil. Here in the top is without light. Without light, in 5 minutes, nothing happened. Why nothing happened? What? There's no light. The oil is viscous. It doesn't go up. What's happening here? Here this is with light. We put it in after 0 minutes, but after 5 minutes, the water is clean because all the oil goes into the sponge. Okay? This is, again, another very beautiful example. This is water, and this is oil. Okay? We put the sponge in, we shine light, and then we can separate the water and the oil. We can actually do it many times, in many cycles. See, these 50 cycles, and what we can see here is this is the oil that was on the water, and this is the oil that we can take out with the sponge. You can see it's always almost identical. We can do it 50 times, which is very important for practical application. Because if we sell this sponge to somebody that wants to clean oil, it's not that he can use it only one time. He can use it 50 times, 100 times. It's very good for practical application. That's it. Questions? So you're going to buy it from me? These things for water desalination? No, I'm joking. I don't have a product yet. I'm not a salesperson. I'm a scientist. But maybe one day, these technologies that I showed you, maybe they will be used practically. Who knows? I'm sorry? Everything that I showed is commercially available. All the polyurethane, all the sponge, all the other materials that are commercially available. The entire thing with the carbon dots is not commercially available. This is still a lab demonstration. Nothing, I don't sell it yet. No, well, in my lab they're using the technology. But it's not that I sold it to somebody yet. But I hope to do one day.
Just like one of the slides you have shown, that CNC plus chitosan.
Yes.
So CNC is like a carboxyl metal cellulose, CNC.
Yes.
So surface is hydrophobic, is supposed to. And chitosan is hydrophilic.
Exactly.
So it's kind of composites they are doing.
It's a good point. Overall, the sponge is hydrophilic. It is hydrophilic because you want the water to go inside. So the relative concentration of CMC is not as high compared to chitosan and the carbon dots, and overall the sponge is hydrophilic.
So just we mix.
Yes?
Without any medicine.
No, well, we add this ECH, which is a molecular cross-coupling. Yeah. I'm sorry? Yeah, I think so. I don't remember. You're a polymer person. Yeah, it is very easy, and you can make the sponge with that, using that.
So cross-linking is going to be physical or
Chemical.
chemical?
I think it is chemical, yes.
And we can reuse it?
This one, yeah, we definitely can reuse it. I think we tried maybe 100 times, 100 cycles. Yeah.
So that may lower the efficiency
Yes.
after using?
Yes. What happens is that over time, you get a lot of ions and pollutants absorbed inside, and it's not so easy to get them out. So over time, it's not going to be so useful. But that's okay, because it's very easy to make it.
Can't we rewash it again and again?
We tried it. We take the gel with the ions, we cleaned it with little water, and then we reused it. So overall, we could use it several times, but obviously over time it is less efficient.
Any questions from student side?
So,
I have also one.
sure.
So, as the role of light, sunlight is just to heat up the carbon dioxide. So, whether the
Not to heat, but to do the photothermal effect. Yes.
So whether have you studied whether the temperature or the intensity of the light also play important role in that?
Absolutely. When you have high intensity of light, you have more light absorbed, you have higher temperature obtained.
So, continuation to that, the interesting fact is that Bilaspur, where you are standing, is the ideal place to perform such experiment. Well, in the summer, temperature goes to 40.
You're right. Yeah.
So you may get similar work, but you may get even better results.
Yeah, and you can get dehydrated also because it's too hot.
What are the basic criteria for being a carbon bond? Like we have so many carbon graphite, diamond. So what are the basic characteristics of being one? What is the size?
It's much easier to make carbon dots than graphite or diamond. Basically, you just take carbon source and you heat it a little bit in 100 and 200 degrees, and that's how you make carbon dots. That's why it's so nice, because it's so easy to make them.
If we heat some compound, it finally becomes charcoal type of thing. So
You're right, but the difference between carbon dots and char is that here, which is actually very important, here you just heat it to 100 degrees, 200 degrees. It's not a high temperature. When you get char, you burn completely the carbon. You go to 500, 600 degrees. That's how you break everything and you get just carbon. But this is not carbon dots. Here, it's very gentle. You heat to a relatively low temperature, 100, 200 degrees, it's not such a high temperature, for a few hours, and then you get carbon dots. That's how you get them.
why this wood is unique property, like photocarbon, what is the origin? Why they are so
The origin of that is the nano size of the carbon dots. Because what happens is that you shine light, you excite the electron. And the electron wants to go back. And it goes back through going out in the material and releasing heat. Because when you shine light, you give energy. You give energy to the electron. The energy needs to go somewhere, and it's just heating the environment, heating the material.
And along with carbon, you are make it also carbon nanotubes.
That's much more difficult to make. I didn't make carbon nanotubes. It's much more difficult.
Like practicing from biomass, you take carbon source. It is possible to make like graphene type material also.
Of course.
Lower temperature like 250 around. It's also possible.
Look, I don't know how to make graphene or graphite sheets. I know it's much more difficult. I don't know the protocol how to make them, but it's not so easy compared to making carbon dots. It's not that you just take carbon and you heat it and you get graphene.
And even it is much more difficult to making it stable at the standing.
I think so, yes. But, you know, at least what you have carbon everywhere. So you can make carbon nanotubes, you can make graphene, you can even make diamonds now. But much easier to make carbon dots.
It's possible if starting material contains some biomass like carbohydrates or cellulose, it may be paralyzed in temperature in 200 to 250. That may convert into light sheet structure like graphene.
Maybe, I don't know. It is, I don't know. I don't work with graphene. I work with carbon dots.
What is the driving force there?
What happens, the driving force is that when you give 100 to 200 degrees, what you do, you break bonds. You break and you break and you break until you reach a stage where you have small nanoparticles. Very small. And then it's more difficult to break the bonds because they are very stable. So that's what you do. You just break and break until you get small nanoparticles. If you give higher temperature, 500 degrees, 600, then you can take everything, break it completely, and get char. But this is not what you get here because you are very gentle. And not so much. That's why I told you can make it at home. Because what we do is you put it, you heat it, then you need to purify it, which is, you do it purification with dialysis or certain simple chemical means, and then you get carbon dots. Anything that you want. Any carbon source. That's the nice thing about it. That's why I show this slide that shows many different things with carbon. You can take the computer and make carbon dots. You can take milk and make carbon dots. You can take flowers and make carbon dots. Everything around us have carbon. Whatever has carbon will make carbon dots. What do you mean size limitation? Of what? No, the particles is nanoscale. That's the nice thing about carbon dots. They're very, very stable. We find that the protocol is actually very stable. In most cases, you get these small carbon dots. Of course, you can control. People work on controlling the size very precisely. When you optimize your protocols, you can make carbon dots with 5 nanometer or 2 nanometer or 10 nanometer. That's possible. But it's not that they make from nano to micro. It's actually very uniform. That's really the nice thing about it. Because you break everything and you get the smallest particles, which is the carbon nanoparticles. Okay. Sorry. Yeah, we can take a break, although we meet again and then I don't know what we're going to do.
Yeah. One nice thing I will tell about Professor Lal, he is also associate editor of a very prestigious journal. So you can utilize this kind of specific people from the research background, how to write papers.
Actually, good idea.
How to get a good journal, published in good journal, what will be the theme.
Okay.
So you can mold the discussion even for your own benefit.
Good idea. Let's show a paper and I'll tell you what is my strategy for writing a good paper.
Yeah, so that will be a benefit of research scholars.
Good idea. Thank you.
In ours,
Yes.
ours,
Yeah, but let's take a break first.
of course, that's much needed.
Yes, yes.
We'll be back here by 3.
15 minutes.
15 minutes.
3:30.